was packed, full of reporters and members of the team. And today, it is packed again with many of the people back for today's news. And it's been actually fabulous and wonderful to see everybody together again. Now, everybody probably knows by now that NASA's Opportunity went silent on June 10th. That's after a massive global dust storm just covered the planet, and the skies darkened, and the rover could not get solar power. Last night, the team made its final planned commands, and we have some video to show you right here. At the time, part of the team went up to Mission Control to send up more commands to ask the rover to respond. One-way light time is about 13.5 minutes. It took 13.5 minutes to get a signal up to Mars. And if the rover did respond, it would take another 13.5 minutes to come back. To find out more and what the outcome was from last night, I'd like to introduce you to the panel right now. We begin with introductions. Our JPL Director, Mike Watkins, the NASA Administrator, Jim Bridenstine, and also the Associate Administrator, Thomas Zurbuchen. Thomas, we'll start with you.
Thank you so much. I was there yesterday, and I was there with the team as these commands went out into the deep sky, and I learned this morning that we had not heard back, and our beloved Opportunity remained silent. It is therefore that I'm standing here with a sense of deep appreciation and gratitude that I declare the Opportunity mission as complete, and with it, the Mars Exploration Rover mission as complete. I stand here surrounded by the team, and I have to tell you, this is an emotional time. I stand here surrounded by a team that before I even came to NASA, I got to know as I watched this amazing entry, descent, and landing, the development, and of course at the center of that were two people. Pete Theisinger, who is right here ahead of me. He's a hero in the world that we live in. And right next to me right here is Steve Squires. You're going to meet him later, another hero for all of us. And surrounded by a team. It's a team that makes success like this. It's a team that creates exploration, transformative exploration for science and engineering. And it's a team that is celebrating here today emotionally. I remember the emotions. I saw that Cornell professor jumping up and down like my 4-year-old at his birthday when entry, descent, and landing was complete. And the rover said, "I'm here." And we're celebrating with emotion. Science is an emotional affair. It's a team sport. And that's what we're celebrating today. I will never forget the amazing work that happened here. It transformed our understanding of our planet. Everything we do and think about in our planetary neighborhood with Mars and elsewhere relates to the research that came from that and the engineering breakthroughs that came from that. And it's really a great honor right now to introduce a champion for exploration and for science, the administrator, Bridenstine.
Well, thank you. Thank you so much, Thomas. It's an honor to be here. I want to say almost 2 decades worth of work by so many extraordinarily impressive people in this room right now. And then last year I became the administrator and Opportunity quit communicating. Can you believe that? So I take full responsibility. But because I'm a politician historically, I will go ahead and pass that responsibility to somebody else. I don't know yet, but I'll figure out who that is. This is a celebration of so many achievements. And I'll just start by saying, when this little rover landed, the objective was to have it be able to move 1,100 yards and survive for 90 days on Mars, 90 sols. And instead, here we are 14 years later, after 28 miles of travel, and today we get to celebrate the end of this mission. So it's an honor for me as the NASA administrator to come out here to this amazing facility with so many amazingly talented people to say thank you for your great work, not just for our country, but for the science that people are going to be benefiting all over the world. They're going to be benefiting from this science for years to come. And so now I'd like to take the opportunity to introduce the director of the Jet Propulsion Laboratory, Mike Watkins.
Thank you, Jim. Spirit and Opportunity may be gone, but they leave us a legacy. And that's a legacy of a new paradigm for solar system exploration. A robotic geologist on Mars and an integrated science and engineering operations team here on Earth all set out together on a mission of discovery. They didn't know what they would find. They didn't know which direction they would go, sometimes from one day to the next. And they made it work. And they made it work longer than any of us thought possible by both brilliant scientific deduction of where to go and brilliant engineering to keep the rovers alive. And that legacy continues, not just in the Curiosity rover, which is currently operating healthily on Mars after about 2,300 days on the surface of Mars, but also in our new 2020 rover, which is under construction here at the Jet Propulsion Laboratory. But Spirit and Opportunity did something more than that. They energized the public about the spirit of robotic Mars exploration. They brought to life these two little intrepid rovers and an incredibly energetic and dedicated ground team. And the energy, the infectious energy and the electricity that this mission created was obvious to the public. And that legacy turns out not only in a generation of engineers and scientists, of which I am one, but also a generation of students. Many students were inspired to go into STEM careers, and a few of them actually to come here to JPL to work on this mission opportunity. Now, you will hear a lot more about these two legacies in the upcoming panels. And to get that started, I'll turn it back to Gay Hill.
All right. Thanks, Mike. And we would like to add that we will be taking questions later on in the program at the end of all our panels. So if you are on the telephone, be sure to hit *1 to get yourself in the queue. If you have a question on social media, use #AskNASA. All right. So let's tell you a little bit about our rover Opportunity. If there were a word to describe this rover, it would be an overachiever. Now think about it. It was only supposed to go 90 days. It went 14 and a half years. And from it, we learned a wealth of science and also how to explore. With that, we give you this overview.
To have positive confirmation of a safe landing. We're seeing it on the LTP.
Opportunity hit a hole-in-one when she landed. The airbag system rolled into the small crater called Eagle Crater. And when the rover first turned on its cameras, it saw that the rim of the small crater was lined with exposed bedrock.
So we took out our microscope for the first time and we took a picture, and the surface of Mars at that location is littered with an uncountable number of little round things.
That were called blueberries because they looked like blueberries in a muffin. What we discovered was that those are features that form in water, and they were a really definitive sign that there had been liquid water on the surface of Mars sometime in the past.
You know, after we left Eagle Crater, we went to Endurance Crater, and that's the crater we drove down in. And there we did what the geologists call an in-sequence stratigraphic section, which is essentially reading the chapters of the Martian history book in reverse order.
That rover became a stratigrapher. First time you had a stratigrapher on Mars. We knew we wanted to go after Endurance to Victoria.
We put pedal to the metal and we started heading there, tens of kilometers away. We had to literally surf across these dunes of wind-blown material, and the rover got stuck in one of those. We had to get the rover unstuck. What we found is the best way to get it out is just to put it in reverse and gun it. The rover eventually popped out. And so we changed our driving strategy. So we recognized these ripples as hazards. We get to this giant half-mile diameter crater, Victoria Crater, and we want to figure out, gee, how can we go into this thing?
All of a sudden we got high-rise images. We could see the rover in the image.
And that was the very first image that we got from space showing one of our rovers.
We spent a year scouting the edge of that crater to decide where we wanted to go in to get the best stratigraphic section.
We found a place to go in, and we drove down in, and we spent about a year inside Victoria Crater.
The science team was really excited about the idea of driving to Endeavour Crater, over 20 kilometers away. This is a long drive to do. It was going to take multiple years, but they decided to do it anyways.
There were too many of these dangerous ripples in our way, and we actually had to take this circuitous route that at times took us away from the crater, only to then cut back and then approach it more directly.
And then we pull up to Endeavour Crater, and all of a sudden there's all these new things to look at.
We first discovered the homestake vein. It was this very, very bright linear feature. It turns out that it was a big gypsum vein, and we see these gypsum veins now all over. So it was our first taste of what is a really important process on Mars.
We were driving to a valley, and along the way there, we realized that right about the point where we were about to get to this valley, that was when we were going to cross the marathon mark. So we said, well, that's cool. We're just going to name this valley after that, call it Marathon Valley. That was when we reached the distance of a marathon, 26.2 miles on another planet. We continued driving through some slopes down a little bit on the interior of the crater rim until we came back out so that we could continue on to the next valley, Perseverance Valley,
where the rover was exploring when we lost contact.
We said we're going to operate this vehicle until the day where we can't, and that's exactly what we did, and I'm really proud.
We've set a foundation that will serve as the basis for future exploration.
Well, Opportunity would not have had that longevity had it not been the engineers that built it and the engineers that kept it going. They took the word workaround to a whole new level. So let me introduce you to Project Manager John Callis and Deputy Project Scientist Abigail Freeman.
Thank you. Thanks, Gay, and good morning. We were meant to get to this point, to wear these rovers out, to leave behind no unutilized capability on the surface of Mars. But we had no idea it would take this long. But even still, this is a hard day, and this is hard for me because I was there at the beginning, and I remember during the early days of development when we were trying to finish up the construction of the rovers in the clean room just a few feet away from here, that we were working 3 shifts. And the engineering team was working the first 2 shifts. And they had one person who would keep a skeleton shift for the rovers from 11 p.m. to 7 a.m. And I volunteered to take many of those shifts, typically on the weekend when it was hard to find someone. And it was very meaningful and very touching because it was just me with the 2 rovers. The rovers were in the clean room like it was a neonatal care facility. And they had all the life support equipment. And you would watch their vital signs, and you would see their heart rates, and you would see the voltages and temperatures and currents, and they would be living. And you would see them wake and sleep. And so during those times when it was just me, you develop a special bond, and they become your children. And that theme, I think, is true for so many people here tonight, or today, that they have that strong connection. So even though it's a machine and we're saying goodbye, it's still very hard and very poignant. But we had to do that. We came to that point. So what happened? Well, back in June, we were afflicted by a historic global dust storm on Mars. It just blackened the skies over the rover and starved the rover for energy, and the rover went silent. And we tried valiantly over these last 8 months to try to recover the rover, to get some signal from it. We listened every single day with the Deep Space Network, with our sensitive receivers, and we sent over 1,000 recovery commands, trying to exercise every possibility of getting a signal from the rover. But with time, the skies are darkening. It's getting colder on Mars. We recently passed through the historic dust cleaning season on Mars to see if that would help. But that brought us to today, or brought us to last night. We set our final commands, and we heard nothing. And so it comes time to say goodbye. But we want to remember the 14 and a half years of phenomenal exploration. This was a 90-day mission, and we were so excited by just having 3 months to explore the planet with just a kilometer of capability But 14 and a half years later and 45 kilometers of odometry, we've done phenomenal things. We've greatly expanded our understanding of the red planet. So, you know, why did these rovers last so long? Why did Opportunity last so long? Well, there are two main technical reasons. One is that we had expected that dust falling out of the air would accumulate on the solar rays and eventually choke off power after about 90 days. But what we didn't expect is that wind would come along periodically and blow the dust off the arrays. And this, on a seasonal cycle, actually became pretty reliable and allowed us to survive not just the first winter, but all the winters we experienced on Mars, and to keep going and exploring. The other thing was that these rovers actually have the finest batteries in the solar system. You know, they have over 5,000 charge-discharge cycles on them, and they still have about 85, or had about 85% of their capacity. I mean, we'd all love if their cell phone batteries lasted this long, but that really was an enabling capability that with the dust cleaning and the batteries allowed us to have that critical energy we needed to get through the coldest, darkest parts of the winter on Mars and to keep exploring. And explore we have. I mean, we've done phenomenal things, and you'll hear about some of that. But we had many challenges along the way. I mean, when we first landed on Mars, one of the things that happened is we have a heater on the robotic arm on the rover that got stuck on. And so every night, that heater would come on and waste energy from the rover. If we left it alone like that, the mission wouldn't have lasted long beyond the 90 days. So we developed this technique called deep sleep, which is every night we would turn everything off on the rover, including all the survival heaters, and the rover would get cold, but it would stay just warm enough that in the morning when the sun would come up and we would power everything back up, it never got below its allowable temperatures. You know, this is kind of like you have the light in your bedroom is stuck on and you can't sleep, so what you do is you go outside and you turn off the master breaker for your house, but that means your refrigerator starts to warm up. But you know, by the morning time, when you wake up and you turn the breaker back on, the ice cream hasn't melted too badly. And you do that every single night. Now imagine doing that for 5,000 nights. And that's what we had to do for this vehicle. But it also partially perhaps explains why we weren't able to recover the rover. Because with the loss of power, the clock on the rover gets scrambled, and it wouldn't know when to deep sleep. And so it probably wasn't sleeping at night when it needed to, and that heater was stuck on, draining away whatever energy the solar rays were accumulating from the sun to charge those batteries. So that might be part of this explanation, in addition to the fact that now it's much colder and darker on Mars. But we had many other challenges. Many of the people in this room know. You know, we suffered from amnesia on the rover, where the flash memory stopped working, and the vehicle wouldn't remember anything past shutting down and sleeping at night. So we had to make sure that we got down every day all the critical science information we collected that day. And we did that for many years on this vehicle. So all those things were accomplished by a phenomenal engineering and science team. We were innovative in problem solving and figuring out ways how to keep this rover going and how to keep it productive and to continue that exploration and scientific discovery. The fact that we lasted so long also meant that, you know, we lost some people. Sadly, some of our colleagues passed away. But many people moved on to other things, other projects and other endeavors. And so we had to replace those people. And we hired in many young people onto this project and trained them to be experienced engineers. We had literally a pipeline of training young engineers to be phenomenal contributors for their careers going forward and here at JPL and for NASA. And that's been one of the rewarding legacies of this project, is that we've produce a generation of scientists and engineers that can go on to do even greater things. So I'll turn it over to our deputy project scientist to say a little bit about this dust storm and some of the science we did. Abby?
Sure. Thank you very much, John. If we could show the graphic of the dust storm. This was a historic dust storm, and we needed a historic dust storm to finish this historic mission. Up on your screen, you can see a simulation of what the sun usually looks like. So all the way on the left, where there's a really bright sun, that's a typical summer day on Mars. In the middle of the image, that's about as dark as the sun got in the previous dust storm both Spirit and Opportunity experienced in 2007. This past dust storm, we could tell that the sky got as dark as what you see all the way on the right-hand side. The sky was so dark we couldn't see the sun, and these solar panels couldn't recharge the battery. I'll speak a little bit to John's statement about the legacy of this rover. When Opportunity landed back in 2004, I was actually in high school. I was a high school junior, but I had the amazing opportunity to come to JPL and actually be here when the rovers landed. I was a participant in an outreach program sponsored by the Planetary Society. And I was actually in this room on landing night. There I am. Standing right over there for the press conference, but that's a picture of me with the science team seeing the first images come back. And it was those first images from Opportunity that inspired me to become a planetary scientist. They revealed a view of Mars that we had never seen before, and I was in the room with the folks who were so excited to see that bedrock in that crater, and I wanted to know why. You know, I've been hearing a lot of people's stories, both from within the project, from within JPL, and from all over the world via social media. And what strikes me as so cool is that this story is not unique for me. There really are hundreds, if not thousands, of students who are just like me, who witnessed these rovers and followed along their mission from the images they released to the public over the last 15 years, and because of that, went to pursue careers in science and education and math. So thank you all so much, and I'll turn it back to you, Gay.
All right, thank you, Abby. We're just going to take a beat. Could I just get a show of hands of how many of you here happen to be in high school or below? How many have you been here since the very beginning of the mission? This is fabulous to see that it has on through generations. This is so cool. When we come back, we look at the scientific discoveries.
One of the other things about this project that's been a truly unique opportunity for everybody involved is the people that have been involved with the entire process. Yes, the project is about a robot, but the reality is that robot was built by a bunch of people.
The reason this thing has lasted so long goes back first and foremost to the people who built them. There was a team of engineers at the Jet Propulsion Laboratory, at some other institutions as well, but primarily JPL, that 19 years ago were given a task that many people thought was impossible. That group of engineers built these extraordinary machines. The reason that missions in Spirit of Opportunity, instead of being 90 days and driving half a kilometer across the Martian surface, turned out to be this more than decade-long adventure of overland exploration, is because of those engineers and what they did.
Some folks forget that Opportunity was actually a twin. The Mars Exploration Rover mission also had Spirit that explored on the other side of Mars in a place called Gusev Crater. And just like Opportunity, Spirit went well past its warranty and brought together lots of science for our team. And let me introduce you now to Steve Squires. He is the principal investigator, and Matt Gollenbeck, he's the project scientist, to tell us about some of these findings.
Thank you, Gay. And let me just first say it's so good to see so many of my dear friends and colleagues from the Mars Exploration Rover project, past and present. I love you guys, and it's just great to see everybody. Spirit and Opportunity were robotic field geologists. Geology it's a forensic science. A geologist is like a detective at the scene of a crime. Something happened at this place on Mars billions of years ago. What was it? What was it like there back then? And you're looking for clues, and the clues are in the rocks. And so we equipped these vehicles with the tools that they needed to read those clues. Now, Spirit's mission really began in earnest 156 days into our 90-day mission when we reached the Columbia Hills, this wonderful range of hills that we named to honor the memories of the Columbia Space Shuttle astronauts. And the clues there told us about what Mars was like at this place very long ago, very early in Martian history. Mars today is a cold and dry and pretty desolate world. It's a place where not much happens, okay? But at that place, long ago, it was a hot, violent, steamy place. There was a lot going on. There were impacts, violent impacts that produced craters and crater ejecta. There were volcanic explosions. Volcanic lava would come into contact with water and ice below the ground. It would flash into steam and go kaboom and throw rocks everywhere. We would see those deposits. Most compellingly, we saw profound evidence for hydrothermal activity. Hot water, there was steam vents, things that the geologists would call volcanic fumaroles. There was steam coming out of the ground. There were hot springs. It sounds like a scary place, and it actually was in a sense, but it was the kind of place that would have been very, very suitable for some kinds of very hardy microbes. It's a place that was habitable. Now, Opportunity's mission, Opportunity had two missions. The first one lasted for about 9 years. It started Sol 1. First day that we landed, it was geologic pay dirt right from the very beginning. Now, the story in the clues in the rocks at the Opportunity site was very different. These were somewhat younger rocks, and what they showed was evidence that there had been liquid water below the surface, liquid water that had come to the surface, trickled across the ground, evaporated away. But it wasn't nice stuff. We were running around saying water on Mars, water on Mars. It was really sulfuric acid on Mars, okay? The pH was very low. This is very acidic stuff. It was very salty. This was not evidence of an evolutionary paradise. But it was a fascinating, fascinating environment. And we studied that place by going to a series of impact craters. First, Little Eagle Crater, smaller than this room where we landed. Then Endurance Crater. And then ultimately the long 6-kilometer trek down to Victoria Crater. And we were at Victoria for 2 years, about a year along the rim, another year down inside. And, by the time we wrapped up the investigation at Victoria, we'd been at that point on Mars 4.5, 5 years, something like that. We'd put a better part of 7 or 8 kilometers on the odometer. We had kind of done most of what you could do on these rocks. We had done stratigraphic sections. We had been down into these craters. We had really pieced together a compelling, detailed, scientifically nuanced story of what had happened. But then we had to decide what to do next. And what we could have done, I suppose, was just kind of noodle around on the plains until the wheels fell off, but it didn't feel like the right thing to do. That was not a goal worthy of this rover. It was not a goal worthy of this team. And so we made the decision at that point to do the long, long, long drive to Endeavour Crater. It was, what was it, Matt, 4.5 years, something like that, to get down there, 20 kilometers. It was excruciating. But we got there, and when we got there, the mission started all over again. New rocks, new stories, looking into the very distant past. We were able, at the rim of Endeavour Crater, to find rocks that were probably the oldest observed by either one of the rovers, rocks that even predated the formation of Endeavour Crater, and those told a story of water coursing through the rocks, but with a neutral pH. It was water you could drink. And so we were able to piece together a new story there. That was one of the mission's most significant discoveries. It came 11 years into our 90-day mission. Matt?
So the traverse from Victoria to Endeavour was not excruciating. It was incredibly exciting. So for someone whose day job is trying to figure out where to land spacecraft on Mars, the science behind that is looking at remote sensing data and predicting down what's on the ground. And when we got to Victoria Crater, the world opened up in a way that it never had before with high-rise images, high-resolution images at 25 centimeters per pixel. For the first time, we could see our rover sitting on the surface. And that means you could figure out where to drive it. and have a knowledge that it would be a safe path or not. Now, the distance in line of sight between Victoria and Endeavour was maybe 16 kilometers, but along that path were 70% of the surface included bed forms, large ripples that could eat your rover. And we didn't want our rover to be eaten by a bed form. That wasn't the idea. So we had to figure out a path. And Tim Parker and I spent years looking at the high-rise images, and we came up with a variety of paths. We had the blue path, we had the yellow path, we had the gold path, and finally we had the pink path, and the pink path was the winner. The pink path went completely out of the way from the straight line direction between the two, drove south, and then drove east in a direction where there were not a lot of hazards. And some of my fondest personal memories of the mission were going into the rover team and working with the rover when, sorry, Steve, most of the science team had checked out and said, you know, remind me when we get to an outcrop because these ripples just aren't doing it for me. But to me, it was tremendously exciting to be able to know where you were, relate it to what you saw around you, and help the rover planners decide where to go next. Okay, so that was the fun part. So the question is, what science, what clues in the rocks allowed us to come up with a story of battery acid in the middle Martian history and cleaner water later? And the clues were in the rocks. At Eagle Crater and the earlier locations, we saw sulfate sandstone. So these are rocks with little sand-sized particles, and their composition was largely sulfur, or a large part of it was sulfur. And they were finely laminated and layered. And we started thinking about it, and the way we could get these rocks by was evaporating salty water. And the evaporation that left these minerals were then put into bed forms, sand dunes that moved them around. The water then coursed through the rocks and created the blueberries. So that led us to this story of acid-rich water, which we don't usually think of as being very useful for life as we know it. But when we got to the rim of Endeavour Crater, we saw clay minerals that were aluminum-rich, that could have only formed by pervasive alteration of neutral pH waters. And neutral pH waters, that's the kind of water we could drink, and that's the kind of water that we think life could have gotten started. So this endeavor of going to Endeavour Crater and to exploring with this rover was after one of those almost theological questions. Will life form anywhere that liquid water is stable, or are we really, really lucky? Back to you, Kay.
Some great stories, Matt. All right, when we come back, we're going to take a peek at our next rover. Stay with us.
Parachute deploy has been detected. Radar solution, matrix 21. 3,000 feet. The radar has a positive lock on the ground. We have a retro-rocket firing solution. Retro-rocket ignition on my mark. At this time, the retro-rocket has fired. We have confirmation. Retro-rocket has ignited. We are now awaiting confirmation of positive signals bouncing on the ground. We're getting a bounce signal. We're getting a bounce signal. We're getting a bounce signal. We're seeing it on the LTP. Very strong on our LTP.
Oh, look at this!
That's our next rover. And with us right now is Jennifer Trosper. She gave us that tour. And also Lori Glaze. She is our person who looks over all of the planetary missions coming up. So let's take it away with Jennifer.
Hi, I am the project system engineer for the Mars 2020 rover, and I'll talk a little bit about that and the foundation on which that was built, which happened on the Mars Exploration Rover Spirit and Opportunity. And amazingly, I was the project system engineer on Spirit and Opportunity also, so I have a unique perspective to talk about how those rovers are really a stepping stone for the large rovers that we build today. And I actually gathered a group of folks, there's Rob there, and some other people, I don't know if they're here, and we talked about what we thought the real legacy and the stepping stones that Spirit and Opportunity did for us that helped us build the Mars 2020 rover as well as the Curiosity rover. And we came up with a couple things that I want to talk about today. The first one was that we went from being stuck to being unstuck on Mars. And what I mean by that is we had Viking landers, we had the Pathfinder lander, we even had the Sojourner rover. But we weren't able to get to the things that we saw in the distance. We saw mountains, we saw rocks, we saw stuff that our geologists wanted to get their hands on, and we couldn't get there. And so one of the great paradigm shifts of the Mars Exploration Rover Spirit and Opportunity was we took everything that we needed, we put it on wheels, and we made a geologist that could go and investigate the things that the science team was interested in. And so you can see that here with the model. This is a full-scale model of Spirit and Opportunity. They were twins. The stuck heater was just Opportunity, but Spirit and Opportunity looked a lot alike. And the things that we took with us that made it so that we could explore, you can see our communications antennas, a high-gain antenna that would track Earth, a low-gain antenna, a UHF antenna that would talk to the orbiters. You can see the wheels that would take us everywhere, the cameras that would show us the interesting places, and then this robotic arm that would abrade rocks and would tell us what the rocks were made of. And that was what our geologist was doing on Mars, a huge paradigm shift for us. The next thing that was significant in terms of building blocks of how we do business here at JPL was the need to do things faster. We had a couple requirements on Spirit and Opportunity that forced us to do things faster. You heard the prime mission had to be completed in 90 sols, which is 90 Martian days. That's not a lot of time to do all the things that we needed to do. We also had to build the vehicle and get it on the launch vehicle in 3 years, which we really figured out and have used a lot more as 3 years and the time to get there. But, 3 years we had to get it built. And I want to talk a little bit about the 90 sol mission and what that made us do in terms of our design thinking and what we put onto the rover. So 90 sols, if we were to try to operate the rover the way that we operated previous spacecraft and gave them a sequence every 2 weeks, we would never have been able to accomplish the mission that we needed to do in 90 sols. And so what we had to do was we had to take all the things that the ground operators would normally do and code them in the software, put high-level behaviors and autonomy on the vehicle, so every day we could tell it something like, drive over there, and it would safely do it, and it would get there on its own. And we could tell it just the times we needed for the communication windows, and it knew how to configure. It had a behavior that would configure all the communications windows. Those things were fundamental to being able to do this mission quickly, and we use them today on Curiosity. We use them on Mars 2020, and Mars 2020 is taking the next steps on things like auto navigation, right? We're making a new algorithm that allows us to autonomously navigate in even more complex terrain so we can go where there are more rocks. We have another processor so we can go faster. We're moving all these things forward, and so this autonomy really started with the Mars Exploration rovers, and it's continuing on today. So then I have to share one of my, I won't say favorite, most memorable moments from the Spirit and Opportunity missions. And I know a lot of you here who were there at this time probably have this as one of your more memorable moments. If you remember, shortly after Spirit landed, 18 days into the mission, we lost communications with Spirit. I was a Spirit mission manager. I was there that day. We did not know what had happened. We were trying to figure it out, but we could not get communications from the rover. And there were a number of us trying to figure that out. What made it more harrowing was that Opportunity was careening in towards Mars, and we weren't sure if we had a problem that was going to cause a problem on Opportunity and Spirit. So instead of being 2 for 2, we were going to be 0 for 2. And so a bunch of us stayed here for 3 days. I see Glenn back there. Didn't go home, tried to figure this out. The good news is, we figured it out, we saved Spirit, we saved Opportunity, and here we are today 15 years later. But the story I want to tell is when I was riding down in the elevator with Dr. Alachi after all that happened, working with these people, and there was a group of folks who had been working those days to try to figure out what was going on the rovers with me. And I had two really significant feelings. The first one was obviously relief that we had kind of glove-saved this rover from, the grave. But the second one was I looked around at the people around me and I thought, wow, what an opportunity for a farm girl from Ohio to be surrounded by such amazing people, a privilege to be part of a team that people could rise to this challenge and solve these problems, whether it was the Spirit Sol 18 anomaly or even just the team today who's trying to get Spirit back, or not Spirit, well, I don't know. Why don't you guys work on Spirit too? Yeah. Go Spirit! Yeah. There was kind of a funny competition between Matt Wallace, the Opportunity Mission Manager, and me, the Spirit Mission Manager, but we won't get into that. Anyway, I want to end by thanking the team from the beginning, the team from the middle, the team from the end for all the work that they did. It's a privilege to be part of that team. And now I will hand it over to Lori Glaze from the Planetary Science area of NASA headquarters to talk about future Mars missions.
Great. Thank you so much, Jennifer. Appreciate it. So Jennifer talked a lot about the engineering legacy of Spirit and Opportunity, which is absolutely incredible and enabling a lot of future exploration. But I want to talk a little bit more about the scientific legacy of this incredible mission, of the Mars Exploration Rover mission. These two rovers really did change the way we think about doing planetary science on the surface of other planets. I love listening and watching Steve Squires get so excited about the ability to actually roll right up to the rocks that we want to see, roll up to them, be able to look at them up close with a microscopic imager, bang on them a little bit, shake them up, scratch them a little bit, take the measurements, understand what the chemistry is of those rocks, and then say, well, that was interesting. Now I want to go over there and have that ability to do that. So now when we think about doing planetary science, we just automatically, we have this new paradigm where we assume, well, we want mobility. We need the ability to go from here to there. We don't want to just go to one place and sit there and do, just study that one spot. We want to move. And so it was that these two rovers really set that new paradigm for how we want to explore. And in addition to just that ability to move around, the discoveries of these two rovers, the discovery of liquid water on the surface of Mars at a time in the ancient past, has inspired the Curiosity mission that's going on right now, still exploring Gale Crater. When Curiosity landed in the crater where we know there was standing water in the ancient past, clearly a habitable environment, that has then inspired our next exploration, which will be Mars 2020. We've now chosen the landing site for that mission. We'll be landing in Jezero Crater, where we believe there is an ancient river delta, that if life ever did come to be on Mars, there ought to be evidence of it there at this location. And we're so excited about it. We're going to drive around with the 2020 rover. We're going to collect samples. And we're already starting to work on what that next mission is going to be, which will be a Mars sample return mission. We're working with the Europeans on that, developing various concepts that would probably fly at the end of the 2020s to go back to Jezero Crater, collect those samples, bring them back to Earth where we can study them and understand, really get a good sense of what's there on the surface of Mars. And all of this is leading towards the ability to, in the future, eventually put humans on Mars, to get the boots on the ground. But I just want to remind everyone in this room that when we do put humans on Mars, they won't be going alone. They're going to be going along with robotic explorers. They'll be working together, and it'll be the people in this room or the people that you've inspired will be helping to bring both the humans and bring those robotic explorers in the future. I just wanted to thank you all for that and hand it back to Gay. Thank you.
All right. Thanks, Lori. Okay. When we come back, we will get some final thoughts from the administrator and taking your questions.
Hello, my name is Jennifer Trosper, and I am the Project System Engineer on the Mars 2020 project. I'm standing in the spacecraft assembly facility at the Jet Propulsion Laboratory, where we're building up the pieces of the Mars 2020 flight vehicle. I want to show you some of the flight hardware we have in here that's being built right now. To the far left, you can see the cruise stage. The cruise stage is the part that gets us to Mars. Then next to the cruise stage, you see our descent stage. The descent stage does our powered descent when we're landing on Mars. It is inside of something we call the aeroshell, which you can see over here. The aeroshell has a parachute at the top, and the parachute will deploy and slow us down at Mars. And then to the far right, what you see is the heat shield. The heat shield is the part of the spacecraft that faces the atmosphere. It ablates a little and slows us down, and then we jettison it. And then the rover comes down on the bridle, and we land on the surface of Mars. What you see over here may not look like what it is, but this is the beginnings of the rover that's going to drive on Mars. It has the electronics on the inside, but we don't have the wheels on, we don't have the mobility system on, we don't have the belly pan on. All those things are coming in, and over the next several months, we're going to finish the rover. So the next thing we're going to do is take all of the pieces that you see here in the clean room, put them together in the launch configuration, and then we're going to take them through our environmental test. So they'll see all the environments that the spacecraft will see from launch all the way to landing on Mars. And we are on track for a July 2020 launch.
All right, that's our next rover. And with us now is the administrator to talk to us about what's on the future for NASA.
Thank you, Gay. I appreciate that very much. Jennifer, as long as we're going to bring back Spirit, let's bring back Sojourner as well, and the two Vikings. Can we bring them all back? We tried. Oh, yeah. Look, I get it. I bring that up for a reason, because I want to emphasize the legacy of this part of the NASA family. What has been done here at JPL is absolutely astonishing, and it goes back decades. And it's so impressive that because of what you have done here, we're going to be able to do a lot more on the surface of Mars in the future. In fact, when I was learning more and more about Spirit and Opportunity, I got to understand that these two spacecraft on the way to Mars actually flew through one of the worst solar storms, one of the worst solar flares that's ever been recorded. And so they had to actually shut down their computers and then reboot them, which was never intended in their design while they were in flight on the way to Mars. And yet somehow, this agency, in fact, JPL, was able to figure out how to get through that very scary part of the mission with a whole lot of investment and a whole lot of hopes on the line. That's an amazing achievement. I remember this part of the NASA family, and you guys hear me talk about the NASA family a lot. I remember when I was here for the InSight landing just a few short months ago, and we had a downlink from the International Space Station so that our astronauts could actually congratulate the folks in this room, many folks in this room and others that aren't here, on what an amazing accomplishment it was to land for the 8th time softly on the surface of Mars with a successful mission. That's what the NASA family is all about, bringing together all of the pieces of this agency to accomplish very special things. And of course, one of the special things that we have to figure out if we're going to fly humans to Mars is how to deal with those solar flares. Because that kind of an event with a human flight to Mars could be absolutely devastating. So that's one of the reasons we're doing the Parker Solar Probe right now with our heliophysics department to figure out kind of when are these solar flares going to occur and what are the impacts going to be. In fact, maybe even be able to predict accurately enough to know when and how to send humans to Mars and do it safely. Friends, there is a day coming when we're going to need the entire NASA family to come together and say we're going to put humans on Mars, and humans are going to be working side by side with landers and rovers and robots, and it's going to be a whole of NASA. In fact, it could even be, it will be as a matter of fact, a whole of the world approach, because we're going to need international partners. And that brings me to Space Policy Directive 1 that the President signed just, I guess, a little over a year ago now. And what he said is we're going to go to the moon, and we're going to go sustainably. And the question is why? Because when we go to the moon, we're going to live and work there for a period of time. We're going to retire risk. We're going to learn how humans can live on a world that's not our own. And we're going to take all of those things that we learn as an agency, and we're going to apply them to Mars. We're going to replicate as much as possible what we learn at Mars. And friends, it's only going to be possible because this entire agency, this important part of the agency, this part of the NASA family, the Jet Propulsion Laboratory, was blazing this trail, is currently blazing this trail, not just with Spirit and Opportunity and Sojourner and Viking 1 and Viking 2, but now with Mars 2020, and eventually a Mars return mission where we're going to be able to look at samples and determine if there's a biosignature in there. Friends, the goal is to discover life on another world. That's what we're trying to achieve. And because of so many great people in this room, friends, we are well on our way to doing that. A couple of things I want to make sure everybody in the audience at home understands. In fact, because of the Curiosity rover, we now know that there are complex organic compounds on the surface of Mars. That does not guarantee that there is life on Mars, but it increases the probability. We now know that the methane cycles on Mars are commensurate with the seasons of Mars. That doesn't guarantee there's life on Mars, but it increases the probability. We know that there's water 12 kilometers, liquid water, 12 kilometers under the surface of Mars. All of these things collude to say there is a lot we need to learn, and friends, we're going to do it quickly. And your legacy here at JPL and part of this NASA family is critical to achieving those objectives. So once again, thank you for having me. Congratulations on an amazing Opportunity mission. And Gay, back to you.
All right. Thanks, Jim. So I must apologize. We do have a hard out on this program. We will need to be off the air at about 11:59 Pacific time. So I'm going to go ahead and ask for all the panelists and speakers to come on up. And we're going to take some questions. Now, if you are on the telephone, go ahead and hit *1. That'll put you in the queue for questions. And also, if you have social media questions, you can have #AskNASA as a way of getting your questions in. Again, we only have a few minutes. I want to promise you that we will still take your questions, even though we are off the air. We have speakers standing by to take your questions, either by phone or online. So we will answer your questions. Let's see if there's any questions here in the room. If not, we will go to the telephone. Do we have any questions? Oh, we do have a question here in the room, right here in the front, third row.
Hi, AJ Esrael from the Planetary Society. A question for Jennifer and Steve and John. Since you all were there at the very beginning, what are you taking with you, Jennifer, to 2020? Steve, what will you be taking from this mission onward? And John, same question.
I'll start with two things. First, people. All of these people are well trained to become engineers on 2020, and I'd love to have every single one of them helping us build the next rover. And then, you know, for me, it's the family. It's the family of the people who helped to develop this, and we work together towards the next missions. And it's not just this team, but the team who worked through all of it. The teams are the part behind the rover that make these rovers great.
Well, for me, when I started out a long time ago on the Mars Exploration Rover project, I was a rookie PI. And I made a number of silly mistakes. Pete, I'm sure you remember a few of them. I learned from those, learned a lot, and have tried very hard to pass some of the lessons along to younger scientists, younger engineers. And then I would completely agree with Jennifer. It's really all about the people and this extraordinary group of people that's in this room, the ones that we've lost along the years. That's the real story, is the people on this project.
And for me, it's the privilege and the honor to have been part of this project, and the honor to have been serving as project manager for the last 12 years that I'll take with me.
I have a follow-on with Matt Gollenbeck, from Pathfinder to MER and beyond.
It's so this project I've been on this project 18 years. And from the development cycle, looking at the landing sites, all the way through operations, that's been half of my career. It's, you know, it's been great.
Do we have a social media question?
We certainly have had quite an outpouring of love online, lots of memories with the hashtag #ThanksOppie, and quite a few people would like to know if we would ever try to retrieve the Opportunity rover and perhaps put it in a Martian museum.
take that one. I've been to Antarctica a number of times, and I've been to some of the huts that were built by the early expeditions that went there more than a century ago, and they're left exactly as they were when the expeditions ended. You can go in there and you can walk into the hut, and the plates with the seal blubber are still there. It's exactly the way that we left them. So I personally would like to see these. We built them for Mars. That's the place that they were designed to go. That's their home. That's where I would like them to stay. Also, if you had the opportunity to bring 180 kilograms of stuff back from the surface of Mars, the last thing I want to bring is something where I know exactly what it's made of.
All right, let's see if we have another social media question.
So Nathaniel Avery on Twitter would like to know, what are some of the new questions we can ask based on what's been learned by this mission?
So I'm happy to take that. Great question, Nathaniel. Yeah, so Spirit and Opportunity have so advanced our ability to ask questions about Mars. Back in 2004, we didn't even know if there had been liquid water on the surface. These rovers answered that question. They revealed some of the details about the timing and the chemistry of that water. And we're asking more sophisticated questions. Curiosity was sent to answer the question, okay, there was water, was it habitable? We've now found, as the administrator mentioned, yes, it was. There were organic molecules. It was drinkable water. As we move forward, we're now asking more complex questions. Okay, Mars was habitable. Where's the life? That's part of the reason we're getting the samples. But we're also interested in understanding why Mars's climate changed, what governs its habitability over time, and perhaps how does that relate to the planets we're finding in our own solar system and all across the universe in other solar systems.
All right, we have a caller on the phone. I believe it is NASA Watch. Go ahead.
Keith Connick from NASAWatch.com for Steve Squires. Steve, as you guys drove these twin rovers across Mars, you'd stop at various places and give them names that evoked exploration, mostly polar exploration, ships and places and people, and one place was named after our mutual friend, Bob Wharton. How would you place Spirit and Opportunity in sort of the pantheon of exploration vehicles such as Endurance and Endeavour and the Beagle and the Challenger? Were they scouting parties? Are they what would you call them in that sort of context?
That's a tough one, Keith. I'm probably the worst person in the world to ask questions about the legacy of this mission. I'm just too close to it. I do have a long-standing interest in the history of exploration. I teach a course on the history of exploration at Cornell. It's something that's very meaningful to me, and I hope that our place in that pantheon, as you said, it turns out to be an important one. But for me, on this day, at the end, it's just too hard for me to judge.
All right, we have another call on the phone. It's from the Atlantic. Go ahead.
Hi, this is Marina Corin. Thanks for taking my question. I'm curious what you all think is the future of rovers on Mars in general. After Mars 2020, do you want to send more to do similar exploration? I mean, should NASA send more, and why?
I'll take that question. Thank you. There's definitely a future beyond 2020. As I mentioned, we were collecting samples with the 2020 mission, and we absolutely want to get those samples back here to Earth. And that follow-on mission will do some additional exploration and then collect the samples and bring them back. And I expect that the 2020 mission is going to guide us towards what the next mission to Mars is going to be after the samples are returned. And so I see a very long and sustained presence at Mars and a sustained exploration there, as well as the rest of our solar system, to help answer these big questions about how the planets formed and how did life form on Earth, and did it form in other places in our solar system. So I definitely see some future exploration coming up.
All right, well, we promised NASA that we would have a hard out on this program, so we're going to wrap questions right now, but we will take more online and on the phone later on today. Before we go, we would like a round of applause for all the scientists and engineers who have been on this mission for 15 years and more.